Dr. Panayotis Mertikopoulos. He is at CNRS and the Laboratoire d'Informatique de Grenoble. And also recently I learned at Criteo AI Lab. And today he's going to talk to us about 2 or 3 pieces of work. And they've done some great work in the area of min-max optimization. And I was promised ODEs and I was promised dynamics, and I'm very excited. So Panayoti, welcome, and the floor is yours.
All right. Thank you so much, Yanni. Thank you also, Simon, and the other organizers for this very kind invitation. Hope to also visit Montreal physically sometime soon to see you again, guys. Physically. Until the time, it is all virtual. So yeah, this talk is going to be about games dynamics and both min optimization and min-max optimization. And well, given the audience of the seminar, I don't think I have to go into too much motivation of why these two particular problems are of very high relevance to the ML and AI community. More traditionally for minimization problems in machine learning applications since basically its inception, and saddle point problems that have seen a real explosion of interest recently, ever since well, all the adversarial machine learning models revolving around GANs and robust RL and all recent developments. I am not going to present an application-focused viewpoint, so I'm not going to zoom in on particular applications to GANs. I'm going to try to give a theoretical overview of some results and some lessons that we've learned, and that I've learned in dealing with optimization methods for this type of problems. And much of what I'm going to present today is work in progress still, despite some existing papers and some existing preprints. So I'm super eager to have your feedback. If you want to throw stones, well, physically you can't throw stones, so I'm safe, but virtually and all that. And I'm hoping to get, as Ioannis was explaining to me, that there is a debate phase after the talk. I'm hoping to have a more in-depth discussion of some of the results then. Anyway, all the preamble aside, the two basic problems, the two archetypal problems that we're going to speak about are minimization problems and min-max optimization problems, continuous both, and actually, for most of the talk, we're going to be dealing with stochastic minimization problems and stochastic saddle point problems. All right, with, of course, the assumptions to come at a later slide. If you want the overview, what I'm trying to summarize in this talk is some conclusions or some high-level takeaways for the long-run behavior of first-order methods when applied to optimization, to minimization problems, games, and min-max optimization problems in particular. And two of the overarching questions, if you want, are from an optimization, from a minimization perspective, if you want, whether first-order gradient-based algorithms always converge to critical points and whether they select local minimizers, and whether in min-max optimization, whether basically the same lessons apply, whether gradient methods converge to a saddle point. What are the convergence candidates, if you will, for min-max optimization methods, and whether non-equilibrium sets or non-saddle point sets are avoided in this case. And the glue, if you want, that will hold this whole thing together is, as Ioannis was saying, the theory of dynamical systems and ODEs. And basically, we'll have a trajectory going from discrete time algorithms to continuous time dynamics, and then back again to harvest some properties that we get along some properties that we derive along the way from continuous dynamics. And at this point, I should say that this line of research has been ongoing for some time now. It started with a joint paper with Zhengyuan Zhu, who is currently in NYU Stern, and then from a very fruitful visit in EPFL, where I had the good fortune to work with Wolfgang Jever, Nadav Halak, Yaping Shi, and Ali Kavis, and some of the more recent results are based on joint work with them. All right, so I'll get right into it and say the main difficulty that we're facing in this type of problems is, first of all, that we're not assuming, I will not be assuming any convex structure of the problem. And I am not going to assume any white box knowledge of the function to be minimized or otherwise min-maxed. So the lack of convex structure and the difficulty to manipulate f in closed form which will force us to use black box oracle methods, are two of the basic difficulties that we encounter. So I should state right off the bat that we're not going to be looking at global optimization properties like global min-max or global minimum points. We're going to be focusing on first-order stationary points. So zeros, if you want, of an associated vector field that is derived from these dynamics. In the case of minimization rather problems, this is just going to be the gradient field of the function to be minimized, and in saddle point problems, this is going to be the individual gradient field of the dynamics of the saddle point objective. All right. So some assumptions that I'm going to use throughout the talk. So I'd rather get them out of the way now. So if there are any questions, let's now is the time to ask about them. They are pretty generic. The first is we're going to be talking about unconstrained problems. I would have to say here that the playing field for constrained problems can be quite different. So I will not say that the things that you see here or the things that I'm going to be talking about carry over verbatim to constrained problems. But for the purposes of this talk, and since we only have an hour, this will suffice. I will also be focusing on problems where solutions exist. So the critical set or the saddle point set of the function is non-empty. And in terms of regularity, I'm going to be assuming that the function to be minimized or min-maxed is Lipschitz continuous and Lipschitz smooth. All right, so these are the basic assumptions that will hold essentially throughout the talk. So,
Yotti?
Yes, sir.
There's a question by Simon. Go ahead, Simon.
Yeah, thanks, Ioannis. So I was wondering, will you just focus on these critical points with zero gradient, or you will also look at the whether it's a local min or a local saddle point, or like you look at the curvature around it?
Yes, we will. We will consider saddle points, escape of saddle points in optimization, but this later. Yeah. So very good question. When if in the end you see me forgetting anything about it, feel free to shoot back again about it. All right. Okay. So the most basic algorithm that we have here, and which is the first thing that we always implement, and I'm going to present it from a minimization viewpoint because it is easier to draw figures that way, is the simple gradient descent algorithm where you start at a given, oops, why can't I do this? Well, okay, you start at a given point, you take the gradient field or individual gradient field along the point, and then you take a step along it. All right, simplest possible method, ancient, not much to say about it. A more interesting, perhaps, method along these lines is the so-called proximal point method, which was popularized in the 70s by Martinet and Rockefeller. which is implicit and hence quite more difficult to implement, because instead of taking a gradient step along the gradient of the point where you currently are, you're trying to guess the gradient at the point where you would somehow end up to, and take a gradient step along this future anticipated gradient. So as a method, this is mostly theoretical. It is very difficult to implement it in practice, except for certain problems. But it is very useful also to build theory and guide very many research threads. A proxy for this implicit proximal point method is the so-called extra gradient method of Korpelevich, which is attempting to anticipate this this proximal gradient by first generating a leading state from the base state. So you take an ordinary gradient step, you then calculate a new gradient at this leading state, and then you update your original state by taking a gradient step along the gradient that you calculated at the leading state. All right. So this is a method which was popularized by Korpelevich in the 70s, then forgotten, then resurfaced again relatively recently, and we have in the audience some of the experts on this method. I don't know. I see Simon. I don't know. I also see Gauthier. So this is a very well known method, and
I see you, Panayotis. You're one of the experts.
Yeah. Okay. Thank you. No, not sure about that, but anyway, thanks. There is also there's also a variant of this method which avoids making 2 gradient calls per iteration, and this is known as the optimistic gradient, which instead of using the gradient at the current state, so instead of using the gradient at the current state to make the update, the algorithm is essentially reusing the gradient from the previous leading state to get the new leading state, and then proceeds as the extra gradient algorithm. All right, so this is an idea that dates back to Popov in the 80s, and then rediscovered by Chiang et al. In 2010, then Rachlin and Sridhara in 2013, then also used again by Gauthier and Simon in various works, and in certain cases, it is a very it has a very good performance properties, and it is essentially a state-of-the-art method. And also there are lots of variants of these methods, like alternating variants, which are valid for min-max problems, where there is one player updating first, then another player is updating based on the new state, including the information of the information update of the first player. Or there are also so-called K-to-1 algorithms, where player 1 maybe takes K gradient steps before player 2 takes 1 gradient step. And in a certain sense, this was also the original method proposed by Goodfellow in his Gunn paper, where he was assuming that the first neural net was running stochastic gradient descent for very many iterations to get convergence, and then the discriminator makes an update. There are also many other methods like Chambol-Poc from optimization, etc., etc. I just wanted to mention all these because these are all different methods. They have you will see different analysis of these methods, etc., etc. And I would like to see in this talk what we can expect from these. From all these methods in a general minimization or min-max optimization setting. So before going forward, I would simply like to make a point regarding the type of feedback that we have that we are using to run these algorithms. And I would like to state that I'm not going to be focusing on the case of perfect gradient feedback, deterministic gradient feedback, because in many cases, in machine learning, in reinforcement learning, and in applications to bandits, this is something which is quite difficult to calculate. So I'm going to be assuming throughout that we only have access to a stochastic oracle. I will come back to this. But for now, just keep in mind that instead of making an update based on perfect gradient information, we are updating based on some noisy, perturbed version of the gradient, including perhaps some non-zero bias. And we will see where this becomes important. Well, actually, one case where this becomes important is in the so-called zeroth order optimization methods, where you are not assumed to be able to even calculate even a stochastic gradient of the function. So this is something which is very important for applications to online optimization. And in this case, you are trying to estimate the gradient by a single observation, by a single query to your function. There is an algorithm that allows one to do this, popularized by Spall and then Flaxman, Kalai, and I think McMahon in the early 2000s, where instead of sampling your function at the point where you would like to estimate the gradient, you are taking a small perturbation of this point, you are querying the value of the function at this point, and then you're multiplying this value of the function with the perturbation that you took and times a normalizing factor, and you're using this as an estimate of your gradient. So this is what is known as an SPSA estimator, a simultaneous perturbation stochastic approximation estimator. Or if you're having similar problems like me and you find simultaneous perturbation a bit difficult to pronounce, I just call it you can call it single point stochastic approximation, which has the same acronym. So why am I mentioning all this? Because the first thing I want to do is to present sort of an umbrella method, an umbrella scheme for all these algorithms, which is the generalized Robbins-Monroe template. And in our setting, what is this? It is basically what we discussed before, where instead of taking a gradient step, you are now including you're now taking a noisy gradient step, where in addition to some zero mean noise, you might also have some bias. Now, is the bias just a technical artifact? If you're looking at gradient descent ascent methods, this bias, if you're running them with stochastic gradients, this bias is typically zero. So a tendency would be to say that, yes, maybe this is something artificial and we don't really care about it. But for all the other methods that I talked about, this bias is actually non-zero. So if you take the proximal point method, well, okay, this is a basically deterministic method, so it has no zero mean noise, but it has a non-zero bias, which is precisely the difference between the future gradient and the current gradient. And you also have the same type of bias in the extra gradient, the optimistic gradient, the SPSA scheme, and the alternating K-1 variants that we also saw. So all this to say that by a suitable definition of the bias of this bias process here, all the algorithms we mentioned can be seen as special cases of this generalized Robbins-Monroe template. All right. So instead of studying each of these algorithms by themselves, I will provide some general results for this GRM template. So how are we going to do this? This is the ODE. This is the dynamics part of the talk, where we're going to start with the observation that this generalized Robbins-Monroe scheme really looks like a dynamical system. I mean, if we divide by the step size, it is almost like we are doing a noisy discretization of a certain dynamical system. These mean dynamics, if you want, of the process. All right, but making this link precise, because it is one thing to say this at a heuristic level, making this link precise is actually takes some technical work and background. The key idea that we would like to formalize here is that if the step size is sufficiently small, then all the errors wash out in a sense, and in a certain sense, the long-term real limit of the Robbins-Monroe algorithm coincides with the long-term limit, the long-run limit of the mean dynamics. In what sense exactly? This remains to be defined. I just want to give the basic intuition, to put the basic intuition out there. So to make the link precise and and explaining what in what sense we can consider this system, the Robbins-Monroe system, to be a discretization of the mean dynamics, we will use the notion of a so-called asymptotic pseudo trajectory. This is something that has been introduced in the ODE method of stochastic approximation by Ben-Haim actually Ben-Haim and Hirsch in their 1996 paper, and which extended previous previous works on stochastic approximation by Jung in the 70s, and then Kushner and Yin in the 80s and 90s, Benveniste and co-authors in the 90s, etc. What is the basic? What are the basic elements of the definition? Well, first of all, you define a virtual time, which is the aggregation of the step sizes, and you define a virtual trajectory, which is essentially the affinely interpolated version of the discrete time trajectory of a Robbins-Monroe scheme. And then what you're saying is that this is an asymptotic pseudo trajectory if this complicated condition holds, which tells you basically what? That you look at the difference between this interpolated trajectory and a point of the dynamics at some given time. You look at the worst possible such difference over a certain horizon, and you are taking the limit as the starting point, as the starting time goes to infinity. If this aggregation of errors goes to 0, then you say that this process, discrete time process, is an APT, is an asymptotic pseudo trajectory of the continuous time dynamics. Intuitively, what does this mean? It means that xn, that the sequence generated by the Robbins-Monroe algorithm, tracks the mean dynamics with arbitrary accuracy over windows of arbitrary length. All right. So just to address the elephant in the room here, I know that this is, if you haven't seen this definition before, it is a lot to take in. So just consider it as a technical condition that we will try to verify in order to get some good results for the algorithms in question. So I'm going to state some results, taking as granted that a certain process is an APT, and then I'm going to prove that this particular process is an APT. All right.
Panayoti.
Yes, sir.
Before you move on, I have a question, and I see 2 more hands raised. So
Yep.
let me first clarify. So this, you're looking into the tail, right? You're looking into the asymptotics. So you're saying
Yep.
you're taking the starting point t to infinity, and then you have this other variable, which is uppercase t. And there was a question from Florian, essentially, what's the relationship between small t and big T? And I have the same question also.
All right. So small t is the starting point. So big T is the horizon, the window over which we will be comparing the trajectories, and little t is the starting point. So what are we doing? We are looking at the evolution of trajectories, of continuous time trajectories, I mean of the mean dynamics, that start at t. This is what complicated flow notation means. All right, this means you're starting at x of t, the same starting point, and you are going forward along the dynamics for length h. Okay, and then you are comparing this point that you obtained by following the mean dynamics to the corresponding position of your affinely interpolated discrete time trajectory.
Mm-hmm.
And then you're looking at this difference over a window of size big T. All right. And what you want is the following. You want, in the limit of little t going to 0, so when you start at sufficiently large times.
To infinity.
Exactly. You want this limit to be infinite. You want this limit to be 0 for any window. For any window, where is big T, big T, big T, big T? Yes, for any big T.
For any finite window big T.
Exactly.
Okay.
All right.
I see.
So I want to be clear. This is a technical condition. A priori, it is not at all easy to verify. I mean, first of all, it takes a lot to digest it. You need to draw a couple of pictures. I would love to. Unfortunately, we can't here. If or I don't know. Is there a virtual blackboard option? I don't think so.
Well, there's the Jamboard. We can pull it out at the end of your talk, or
if needed.
Let's take a couple of more questions, because Simon has a topical question also, and I see Manuela afterwards too.
Yep.
Oh, and Gauthier. Wait, we forgot Gauthier.
All right.
Gauthier.
Simon was first.
Was I?
Oh, okay.
Gauthier, it's your turn. I already asked my question.
Okay.
And Manuela. Oh.
So, Panayotis, if the sequence xt converge, this is quite easy to verify, no? Because we are close to the optimum. Everybody stays close to the optimum, so we are good.
Exactly.
Okay.
But just to preempt, because your question is actually giving me it's the perfect segue. I want to say that the APT the APT property is actually used the other way. So you are showing, we will establish the APT property, and from the APT property we will deduce convergence of the discrete time algorithm.
I see. And so my second question: can you deduce a rate?
No.
A convergence rate?
No.
Okay.
In terms of rates, these you will see, and you will see why. We can discuss this at length later. But the APT based analysis is very powerful in order to determine convergence or divergence. But specific rates, especially since we are talking about last iterative, fully non-convex, non-linear problems, this is not something that can be harvested from this, at least from the blanket version of this property.
Okay, and very last question: is there a way to kind of, like, if you multiply by your sequence by t, like you inflate your sequence and you show the convergence, then you get a rate because you have I don't know if you see what I mean. It's okay. I think it's technical, but it's fine. It's fine, I think.
Okay. You can explain me.
I think it's. I wanted to see if it leads something, but probably it's a bad idea. So I can leave my question to Manuela.
All right.
Sure, and that might be an interesting topic for to discuss later. Yes, Manuela, please go ahead.
Just a quick question. I'm just trying to understand. So the virtual trajectory, it depends on n, right? It depends on a fixed iterates capital Xn and capital Xn plus 1.
Yep.
Correct?
Sorry, no. The virtual trajectory depends on continuous time, because remember, Xn is the sequence, so it is a discrete time sequence. And then we are taking an affine interpolation in continuous time generated by this discrete time sequence. So just to be strictly speaking, Xn is a trajectory in continuous time. Big X of little t is a curve in continuous. Big Xn is a discrete time trajectory. I think I said the continuous time. I'm sorry. Big X of little t is, so this guy is a continuous time trajectory generated by a discrete time sequence via affine interpolation. And these guys, phi A, phi H, or phi S of X, etc., these are the orbits of the mean dynamics. Sorry if that was already clear. I just it is because there's a lot of notation. I wanted to make this perfectly clear. Please, I didn't want to interrupt. Please go ahead.
No. So yeah. So but in the definition of the virtual trajectory, there is just one n, right? Just one capital Xn, or is the whole sequence of iterates sort of hidden in the definition of the virtual trajectory?
Exactly. If you want, this is how you define. This is how you define x of t. I should have been more explicit that this definition is valid when little t is between tau n and tau n plus 1.
Okay.
Okay. And then you go on.
Okay. Then everything is clear now.
All right.
Excellent. Simon, I see your hand is still raised and you left you for last. Sorry about that. You want to ask?
Last but not least.
Sure. I mean, it was just a quick question because it's related to what Ioannis was mentioning. So you said you wanted arbitrary length because you will want this limit to go to 0 for all t, but
for all big t. Yes.
Yeah. Okay. So if t was changing with little t, then you would have issues, but you fix capital T, and so.
Yes. It is important. It is important to take this particular order of the limits, because the other order of the limits would I mean, you can define it, but you would not be able to use it to draw conclusions. And to be clear, the order, whether you take the lim sup or the sublime, is very important here. So this is a very good remark. All right. Yanni, shall I go on? I see you thumbs up, so I'm going on.
I think we're good. Yes.
Okay. So addressing the elephant in the room. When is a sequence generated by a Robbins-Monroe algorithm an APT? So I'm going to present two conditions. The first type of condition, which I'm going to be calling A-type condition, A-type conditions has to do basically with the primitives of the game. The second type of conditions will have to do with the algorithm and will be somewhat, in a sense, trajectory based. So I'm going to discuss them at length, and of course, I expect there will be more questions about that. So first things first, regarding the primitives of the game, I am going to be assuming, as before, Lipschitz continuity and Lipschitz smoothness of the objective, and also a weak coercivity, not co-coercivity, a weak coercivity condition, meaning that the inner product between v of x and x becomes non-negative for sufficiently large x. All right, so these are the two structural assumptions that we're going to be making. And the second type of conditions that I'm going to be assuming, at least for now, is that the bias goes to 0, the bias of the algorithm goes to 0 with probability 1. The bias is also summable in expectation, and also the same holds for the algorithms for the variance of the oracle. All right. So these are the two sets of conditions that I'm going to be using, and under these conditions, I'm sorry, this should be 1996, not 1999. Well, there is some technical work to be done, which I'd be happy to get into later if you want, but is perhaps not the now is perhaps not the best moment for it. But under these two blanket conditions, you can show that the sequence of iterates generated by any Robbins-Monroe scheme is an APT of the mean dynamics with probability 1. All right? Okay. So the problem, if you want, is these conditions, the B-type conditions here, because they are somehow algorithm dependent and not obvious how to verify. So instead, yes.
Since you're moving to the next slide, let me give Florian the opportunity to ask his question.
Yep.
So I'm just unsure. Like, I mean, of course, the first example that everyone thinks of is always this bilinear example. I guess in this case, if one were to cut it off outside of a compact set. But in this case, right, for example, if one takes the simultaneous gradient descent dynamics, they will stay on the circle, whereas any discretization will sort of like move away from the circle.
Right.
So how can this then be APT?
So Florian, this, I don't know if you can see here. No, I cannot highlight. If you look at the top of the slides where you have min-max optimization problems and you see all these little circles, about the middle third of these slides is about exactly this question that you're asking here, here and now. Okay, so let me not. I would like to put this issue on hold, and we'll discuss it. We'll discuss it at length later because it is like super important issue. All right.
All right. Thank you.
Any other questions?
Not that I see. Please.
All right.
Proceed.
So as I was saying, these conditions which are algorithm dependent are a bit difficult to verify. So we'd like to also have some more explicit, well-grounded criteria for this APT property. So this is where we need to dig into the algorithms and the assumptions for the type of gradient oracle that we have. So I'm assuming here that whenever you query the gradient oracle at a given point, you are getting an estimate of the gradient up to a certain error. And for this error, I'm assuming that it is zero mean and that it has well, they should write. I mean here finite variance. So the second moment of this error term is bounded in expectation. All right. So what I would like to point out here that the unbiasedness of the oracle, of the gradient oracle, does not mean that we have non-zero bias in the Robbins-Monroe scheme. So here, what you can keep in mind always is the extra gradient algorithm, where we can run it with stochastic gradients, unbiased stochastic gradients, but still the BN, the bias that enters in the Robbins-Monroe description of the algorithm, will be non-zero. All right. So I just want to be clear that there is a difference between the input signal, the bias of the input signal that goes in the RM algorithm, and the bias of the oracle. All right. And then I would like to discuss the type of step sizes that we're going to be using, which are essentially L2, what is known as L2 minus L1 summable step sizes, meaning that they are summable in L2. Sum of gamma n squared is finite, but the sum of the gamma n's is infinite. So you can do all step sizes between 1 over n and basically 1 over square root n up to logarithmic factors. Now, I would have to say that this upper bound for how aggressive you can be in your step size has to do with the assumption for the mean square error of the oracle, and in particular, if you have a more well-behaved noise like sub-Gaussian noise, for example, then you can go here. You can go here with step sizes of up to 1 over log n to some power or something like that. Anyway, under these explicit assumptions, so under the A-type conditions that concern the primitives of the game and these C-type conditions, what you have is that any sequence generated by any of these algorithms that I presented in the beginning, algorithms 1 through 5, is an APT of the mean dynamics. Okay, so as far as Florian's question is concerned, this is very bad news because it means that two things behave the same way, whereas they shouldn't. So I'm going to give here a very quick overview of what happens in the case of minimization problems, and I think I'm probably going to go over the 50 minutes, but there were a bunch of questions, so I'm hoping I will have some leeway.
Yeah, we're happy with that.
Okay.
Go ahead, blast ahead.
All right. So just some facts known from the some facts from the minimization point of view. Here, the gradient flow is something which is very well known. It is a gradient flow. It has a strict Lyapunov function, so we expect it to converge to the critical set. And indeed, there were some old results along these lines which showed precisely that in minimization problems, all APTs essentially converge to the critical set of the function with probability 1. but they require an explicit, or rather implicit, depending on your point of view, boundedness assumption. So you need to enforce by hand that the APT generated is going to be bounded. And this is, again, something which is very difficult to verify. But thankfully, this is something that under the same conditions that I presented before, this can also be guaranteed. So under the same conditions that we presented, the A-type conditions for the problem and the C-type conditions for the explicit algorithms, you can show that I will skip the details here. You can show that with probability 1, any limit point of a generalized Robinson-Monroe algorithm is a critical point of the function to be minimized. And not only that, in value, you have convergence to some possibly random critical value of the function to be minimized. All right. So you have this general result. And I think it was Simon that asked the question about whether this is a result concerning critical points or also saddle points or points with curvature. So here we can refine this result. There was some the first result along these lines concerned a so-called hyperbolic saddle points, which are points with an invertible Hessian with a negative minimum eigenvalue. And in this case, there is a result by P. Mantle in the 90s, which states that if you have a hyperbolic saddle point, and the noise basically has a component along all components, all directions in space. So perhaps not isotropic, but there are no non-exciting directions in space. Then the probability of converging to a hyperbolic saddle point is 0. All right, this was P. Mantle's result. There was a result of a different form by Gay et al. In 2015, which was further, I think, there was another paper in 2016, but I'm not sure. Which, well, I don't have the time to go into a lot of details, but it tells you that if you have a sort of trichotomy in the structure of your function, so it is so you either have points with a big gradient or points with a negative minimum eigenvalue, or you are close to some strong local minimum of the function, then modulo some technical assumption, you are guaranteed that after that, with some probability, you will end up generating an iterate which is far from any strict saddle point of the function. And well, the problem is here that if you want this iterate, if you want this confidence level to be very small, so if you want to really guarantee avoidance of saddle points, then you have to wait for a very, very, very large number of iterations. But you can also mix and match these results. You can mix a P. Mantle's almost sure avoidance result with the strict saddle result of Gay et al. And you can actually show that under the same condition for P. Mantle's results, if you have any set of strict saddle points, then it is avoided by any generalized Robinson-Monroe algorithm with probability 1. All right. So in minimization problems, you have a very robust selection criterion in the sense that you are only selecting non-strict saddle points as in the end. So you do have convergence. You converge to a component of the critical set, and you know that this component cannot be a component of strict saddle points. All right. So this is a quick overview of what's going on in minimization problems. Now for the most difficult and most challenging part of the talk, which is the min-max setting. But I don't know if there are any questions. No, I don't think so. No.
I don't see any questions flagged, but maybe we can give people a few seconds. So far, you know, the discussion was how we want to avoid saddle points. Now we're moving on to a class of problems where, you know, those saddle points might be our target, right?
Exactly.
It's min-max optimization. Okay, I don't see more questions, so please proceed.
All right. So here, this recap that you did is excellent because it shows exactly what's going on. In minimization problems, we have convergence to the set of critical points, and we are avoiding spurious, non-minimizing critical manifolds. And the question is whether the same intuition carries over to min-max optimization problems. So whether we're converging to unilaterally stable local natural equilibria, if you want, saddle points in this case, of the min-max objective, and whether we are avoiding spurious non-equilibrium sets, at least with positive probability. All right. So the problem here, and this is another elephant in the room, is that in minimization problems, the mean dynamics comprise a gradient flow, which is very well understood. In min-max problems, the mean dynamics can be arbitrarily complicated. And in particular, we will now need an assorted zoology, basically, of definitions of different type of sets that arise. So first of all, some terminology from dynamical systems. You have a set is forward or backward invariant. Rather, it is invariant if it is forward invariant if its image remains within itself along the dynamics. It is attracting if it is invariant and it attracts all nearby orbits of the mean dynamics. And this, okay, so far these two notions are pretty well known, I guess. The other notion, which I guess might be a bit less well known, is that of internal chain transitivity. You are saying that a set is internally chain transitive if it is attracting and it contains no proper attractors. All right, let me give you an example here. Well, this is an example of an attracting limit cycle. This is a very well-known dynamical system in physics, which can interestingly also be phrased as a min-max game. And you see here that all trajectories are attracted to this red limit cycle. All right. On the other hand, you could also have networks of orbits that are connected together, forming what is sometimes known as heteroclinic cycles or heteroclinic networks, etc., etc. In this case, you could have considerably more interesting and more difficult dynamics, in the sense that this set, which is this attracting set, which is internally chain transitive, may or may not contain proper attractors, and may or may not consist of a single trajectory or not. All right. So just this goes to show the type of new phenomena that arise in dynamics that are not gradient flows. So why I mentioned ICT sets is because these end up being the only candidates, in a certain precise sense, of min-max dynamics. So what you can show is that with probability 1, the sequence generated by any RM method converges to an ICT set of the mean dynamics. All right. This is the implicit version of the theorem, if you want, because it depends on conditions that are not always easy to verify, these B-type conditions. If you take the C-type conditions, which only concern the oracle, and you zoom in on all the class of all the algorithms considered in the beginning, then you can show that with probability 1, the sequence generated by any of these algorithms converges to an ICT set of the mean dynamics. All right. So
a quick question. I think I missed the difference in the statement of the two theorems. So you have the two different sets of assumptions, right? A plus B and A plus C. And what changes in the second case in terms of the...
So in the first case, we're considering any RM scheme. So this is a template result.
Okay.
This tells you if you have a new algorithm that you'd like to study, you can simply check if you can put it in an RM form, and then try to check these B-type conditions yourself.
Okay.
The second theorem does this work for you for the case of all the algorithms we presented in the beginning. So extra gradient, optimistic gradient, alternating gradient, blah, blah, blah. All right?
I got you.
Okay.
Thank you.
Yeah. So now, just as critical points were so in a sense, what I would like to say is that ICT sets can be seen so far like the critical points of, as analogous in a sense to the critical points of minimization problems. And like, just as in minimization problems, we have saddles, hyperbolic saddles, strict saddles, we need to define this also for ICT sets. Now, the problem is that, as you said, Yanni, we like saddle points in min-max optimization. So we cannot use the terminology saddle points, and we need to be very careful about how to define it. And the way, at least one way of doing this is by taking into account that any ICT sets possesses what is known as a stable manifold and an unstable manifold. And trajectories along the stable manifold will converge to the ICT set, whereas trajectories along the unstable manifold will diverge from it. All right? So there is, of course, some math that goes into, I'm sweeping under the rug to define these notions properly. But if you want, under the type of avoidance results that you can get here is that if you have a min-max objective, which is Lipschitz continuous and Lipschitz smooth, and you have basically the same assumptions for the noise that you had in the in the minimization case, then you can show that the probability that you will converge to an unstable point or to an unstable periodic orbit, because again, here we have periods again, we can have much more complicated attracting sets, then the probability of converging to an unstable periodic orbit or point is precisely 0. All right. And this is the last thing I want to say before starting to address Florian's question, is that in a sense, this gives us a landscape which from a very high level would seem qualitatively similar to the minimization landscape. So if you take components of critical points, these are analogous to ICT sets, and avoidance of strict saddles, you map it to avoidance of unstable periodic orbits, then you can say you have the same landscape between min and min-max optimization problems. And you can ask whether there is a fundamental difference here.
We have a question by
Yes,
Gauthier.
I have a question. Can you go back? I think it's going to be simpler if you go back to slide before for the statement of your main result. Even before. Because so if I'm correct, you are showing that you converge to the same point, the ICT set of the main dynamics. But what if the main dynamics doesn't have any ICT set?
I refuse to reply to this question because this is like the next couple of slides. It is not exactly the same thing with Florian's question, but we will have the chance to discuss it in more detail. So let me address it online, and let me also connect this because it's gonna die, and we don't want our computer to die at this point. All right.
And I should have absorbed it earlier. Can you repeat a simple definition for ICT sets?
All right. ICT set is invariant and it doesn't contain any proper attractors within it. All right.
I see.
We'll see
for example, a
examples.
limit cycle, for example, is an ICT set.
Trust me, examples are coming now.
Okay, excellent.
All
Thank
right.
you.
Okay. Any more questions that I can refuse to answer?
No.
All right. All right. So, here, I don't think that Kostis is in the audience, but he gave a talk about min-max optimization problem, and he explained exactly how different minimization and min-max optimization problems are from a white box complexity analysis viewpoint. So here I'm going to try to give a black box answer to this question. We'd better hope that it's the same, because otherwise I see Kostis getting angry. So long last, let's see what happens in bilinear games. All right. So here the mean dynamics are very simple to write down. They are linear, and you have an energy function, which is actually a constant of motion if the matrix of the game is symmetric. And the most widely used example of all, the x1, x2 example, where you have these perfect Euclidean cycles where the energy is a constant of motion. All right. So what are the ICT sets in this case? Well, first of all, you know that the type of behavior that you have for the dynamics here is what is known in dynamical systems theory as Poincaré recurrent. Poincaré recurrent means that you can start from any, no matter where you start, after some finite time, you will return arbitrarily close to where you started. Okay, and this is exactly what happens with these periodic orbits. All right, now. As Florian very correctly pointed out, if you do just an analysis of deterministic gradient descent, this constant of motion is no longer a constant of motion. You have a positive discretization error, which leads the gradient dynamics to spiral outwards. All right. On the other hand, if you analyze, well, this should be F, I'm sorry. This actually should be V, I'm sorry. If you analyze the extra gradient dynamics, then you can show that these converge to a solution of the min-max games. So here is the paradox, the apparent paradox that Florian was referring to. On the one hand, you have the mean dynamics, which are Poincaré recurrent, so you have a foliation into periodic orbits. But then if you look at individual gradient descent, you have divergent trajectories, you have outward spirals. Whereas if you have extra gradient descent, then you have convergence, you have inward spirals. So I hear you say, so we have different outcomes despite same mean dynamics. And all this despite me saying that everything is an APT and we have convergence to ICT sets, etc., etc. What is the problem? I wish I had a better slide for this. I'm realizing now that this perhaps does not suffice to give the full picture. But let me first say this, orally, and then I will explain it on the picture. The thing is that the ICT sets in the case of bilinear games are very degenerate, because you have this foliation of periodic orbits. What happens is that any annular region around the origin is an ICT set. Okay, so this means you take any ring of inner radius and outer radius. Perhaps these radii coincide. Perhaps these radii are both zero. All these are different ICT sets of the dynamics. And what the theorem is telling you is that you are converging to n ICT set. So the problem, and this is where we go to Gauthier's question, is not that we don't have ICT sets. Actually, I will show in which sense generically this is having an ICT set is generic. The problem is having too many ICT sets with a structure which prohibits prediction of the behavior of the algorithm. Before going into more detail into this, I would like to also say the following, that this difference in qualitative behavior, convergence versus divergence of the deterministic algorithm is actually very, very fragile. And once you go into the stochastic case, so if you run stochastic gradient descent or stochastic extra gradient, then you basically have the same qualitative picture. You have in both cases, trajectories converge to some periodic orbit at to some non-constant periodic orbit. All right, and this is the precise statement that you can make in this case, that under the conditions, the A-type and C-type conditions we discussed before, all of the algorithms we discussed in the stochastic case, converge to a non-constant periodic orbit. There are, of course, fixes to this. So, for instance, you can make them converge to a constant periodic orbit, namely the solution of the game, if you use some variance reduction method to map it in a certain sense to exploit better gradients, in a sense, or if you use a double step size rule. The first approach was by Shavdarova et al., the other by Shi et al. But at least for the algorithms that we presented, the result is that in all cases you are converging to a non-constant periodic orbit.
Panayoti?
Yes.
We have a question by Florian, and then I also have a question. Go ahead, Florian.
So I mean, I think I understand. I mean, like it makes sense that you have this foliation by infinitely many ICT sets, but I still don't see why you cannot use this to construct a counterexample to the theorem that you showed earlier, that you have this sort of ATP or whatever type of convergence. What
do you mean by a counterexample?
I mean, so you had earlier this theorem that says basically the continuous dynamics and the discrete dynamics will satisfy this lim t to infinity sup over h up to t condition, right? And so now my question is, the bilinear case, I mean, the only possible thing that excludes the bilinear case is Lipschitz condition. So for this one, would have to basically have bilinear in a compact set and then try to continue in such a way as to not violate coercivity. But if that were possible, then wouldn't that be a counterexample? Because in this case, the sort of gradient dynamics, the continuous dynamics would stay on this limit set, whereas the discrete dynamics would be pushed to basically to the outside, where we at some point cut it off in a coercive way.
Sorry, just to be clear, I will address only first the technical point of what you said. It is not coercivity is not the problem for bilinear games, because bilinear games
Lipschitz is the problem.
Yes, Lipschitz continuity. Okay.
Exactly. So that's why I won't have to basically have something as Lipschitz in a compact and then outside cut it off.
Yes.
So it's still. I mean, I'm just like, I mean, I guess if the theorem is correct, then it somehow says that somehow. Basically, that's a statement about that it's difficult to continue such a bilinear function in a way that preserves coercivity outside of a compact set, because otherwise it would be a counterexample.
No, I wouldn't. At least I don't interpret the theorem in this way. The theorem, if you want, is telling you that you are converging to an ICT set. Okay. Now, as we said, the ICT sets could be any annulus, possibly containing the origin. So there is no counterexample here.
Also, does the outer radius of the annulus have to be finite, or is it allowed to be infinite?
Well, if you allow it to be infinite, you are basically allowing the entire state space.
That's right.
So technically, it is disallowed.
It is disallowed. Okay, so you're saying that all of those stochastic dynamics that you showed us will be contained within some finite radius circle.
So let me be absolutely precise. Okay, the blanket ICT theorem is telling you that the stochastic gradient descent or extra gradient algorithm would converge to some annulus of non-negative inner radius and finite positive radius. So basically, it's not telling you absolutely anything in this regard. Okay.
Well, it's telling you it's not blowing up, right? It's telling you that it's
its distance
from origin is not growing.
I agree. It is telling you that it is not blowing up. The result that I have highlighted, where is it? Where am I? Yes. The result that I have highlighted here is not a corollary of the ICT result. You need to do more work to show what I said, that you are converging to a non-constant stochastic orbit in probability. All right? Okay. So to a non-constant periodic orbit. Probability.
One question for you, Panayotis. So it seems to contradict, but I think I understand why it doesn't. If you go one slide before, like when you have your the energy that increases it's more than one slide before. Even before, I think. Yes, exactly here. So you have this discretization error, and so if the step size were constant, it would blow up to infinity.
Exactly.
But since you have your condition of the summing square step size,
Exactly.
it's bounded.
Exactly. Exactly.
That's why.
Exactly. Exactly.
I think it's also answer your question, Florian. Basically, the condition on the step size, since the step size is going to 0, it is going to 0 close enough in order not to blow up at the infinity.
I see. So that was just a missing condition when you showed the theorem earlier. Like if you go back to the slide that had this lim t infinity and so on. That I mean was when I asked the question.
Where?
I think it's condition A in like Panayotis theorem.
Here.
It's A.
No, like way before. Remember when the question arose? What
it was your first theorem,
t
Panayotis.
and lower t.
Before you described the sets of conditions A and B.
Here.
It's condition B.
Exactly.
Condition. Okay, so you have condition B here, which implies that the step size is square summable, and this is satisfied by this type of step size.
Square summability.
All right.
Yeah, makes sense. I see.
Exactly. So I want to be clear that this does not account for constant step sizes, because if you're running any stochastic algorithm with a constant step size, you know that it is. Oops, what happened here? You know that it is a stationary ergodic Markov chain if you have a constant step size. So you preclude any sort of convergence whatsoever. All right. So I don't know if there are any more questions on this.
Oops, sorry. Yeah, mine's answered now. Thanks.
All right.
I think. Wait. So I heard. No, it's good. Everybody's happy.
All right. So the other thing I would like to discuss is that actually this takes us to the final part of the talk, and which is whether min-max, whether bilinear games provide sufficient guidance in this regard. So the first thing I would like to say here is that these type of foliations of periodic orbits are actually very fragile. So if you take a very, very small perturbation of the of this bilinear game by just this 4th-degree polynomial, which is a 4th-degree polynomial in only one of the variables, what you can show is that now for any positive epsilon, you have a unique critical point at the origin, which is unstable under the mean dynamics, and the mean dynamics are now attracted to a unique stable limit cycle from almost all initial conditions. All right, you can prove this with Poincaré-Bendixson argument and calculating a particular abelian integral. I don't want to go into these details, but you can show exactly this last property here. What does this tell us? That if you take a slight perturbation of a bilinear game, then the trajectories of all Robbins-Monroe trajectories will now coalesce to the same limit cycle. And this is what I'm showing here, where on the left you have the continuous time trajectories, and then on the middle and the right you have the corresponding trajectories of stochastic gradient descent and extra gradient. All right. And I wanted to say something more here, that there is a much deeper principle at play here, which shows that in essence, all examples like the bilinear games where we have this foliation of periodic orbits are in the space of dynamical system extremely rare. And this gets us back to the 60s. This is a result from which was taken by differential topologists. Smale was a differential topologist, and Kupka was a dynamicist, where they showed a tandem, two results which in tandem are known as the Kupka-Smale theorem, and which tell you the following. First of all, the first part is that what I'm saying here is that every generic instance of the mean dynamics has non-trivial attractors. And what do I mean by generic? I mean in the Bayer category sense, so that it is a countable union of, it is the complement of a countable union of open-dense sets. And moreover, that for any C2 vector field, the following properties are generic. Again, in the bare category sense, all closed orbits are hyperbolic, and heteroclinic orbits are transversal, in the sense that stable and unstable manifolds of heteroclinic orbits intersect transversally. So what does this mean in everyday language? That non-attracting periodic orbits are non-generic, that they occur negligibly often. And this very deep result, this Kupka-Smale result, is what is sometimes known as the generic existence of attractors result, and which is why the last result I want to show is a result concerning convergence to local attractors. And here the result is that if you have a local attractor, then for any sequence generated by a Robbins-Monroe generic Robbins-Monroe algorithm, you converge to this attractor with arbitrarily high probability if you start not far enough from it. And again, because this is an implicit type theorem, it depends on these B-type conditions. This should have C, not B. This is a typo. You have the corresponding result for any of the algorithms 1 through 5. Again, even though this could be seen as good news in a sense, there is some hidden bad news here, in that if you take a slightly different perturbation of this min-max game, then what you can do is you can have a stable stationary point at the very near the origin, which is shielded by an unstable stationary set, and which is itself repelling all trajectories towards a stable limit cycle. So in this case, you can show that with arbitrarily high probability, and from basically all the state space except an arbitrarily small neighborhood of the equilibrium equation, all trajectories of all these first order algorithms will converge to this limit, to this spurious limit cycle, and this behavior we will have for any positive epsilon, no matter how small. I think I saw a question.
Yes, there's Simon would like to see slide 49 again.
Okay, slide 49. Yes. There you go.
Simon, if you have a question on the slide, feel free to unmute. And
no, it's just it was because the properties were the equation was there and the properties, but it was so fast I didn't have time to.
Okay, my apologies.
I've screenshot it, so now I have all the time to.
Okay. This precise example is also in the paper. So, and I should say it is not exactly at the origin, the critical point, but it is very close. So yeah.
So let me ask a quick question here.
Go ahead, Ioannis. I have a question after you.
Yeah, thank you, Gauthier. So it seems like you've added this polynomial, which basically makes the whole thing. You don't have smoothness anymore, I think. Is that right?
Correct. Again, however, going back to the discussion with Florian, because you only care about the behavior or the dynamics in some very big compact set, and you don't really care what happens at infinity. What you do in this case is you can multiply everything with an approximate identity with a mollifier. You can mollify everything, and then the theory continues to apply. So
so you're saying this problematic degenerate situation here can arise even if you keep things smooth.
The infinity is not the issue, unfortunately, here.
Right. And does Florian had a comment, I think, about the example?
Yes, this is the similar idea as in Alistair Ledger's paper.
Yes. This is very correct. We are basically having, our papers were posted on archive with like 10 days difference, something like that. So yes, Alistair is considering. I don't think he's considering this exact same game. I think he's considering something different. And
yeah, but I guess the same idea. You have this like
yes,
cycle that
and
is
actually,
shielded from another.
Thanks a lot for mentioning this. I was intending to mention it in the last slide for the conclusions, because what Alistair is saying is he's considering, first of all, deterministic algorithms, and he's defining this so-called class of reasonable algorithms, which is any algorithm that avoids second-order unstable points. All right, and he's showing that for any reasonable algorithm of this type, you can have phenomena like what I presented here in deterministic policies. And what is interesting is that the avoidance result that I showed before is that all these algorithms that we consider are reasonable, albeit stochastic, are reasonable in Alistair's sense. So, look, if there are no more questions, I can just present the last slide, which is simply a recap of what we were discussing. First of all, again, just to restate that this is, if you want, one of the main takeaways, the fundamental differences, some of the fundamental differences between minimization and min-max optimization problems. That in min-max methods, you may have limit points that are neither stable nor stationary. What I find interesting is that in a certain sense, bilinear games can be sometimes misleading case studies for min-max optimization. Rather, they can be very instructive if you're interested in, for instance, in monotone problems or finite games. But perhaps, if you want to work in a much more general class, you have some phenomena that occur there that are, in a sense, in a bare category sense, rare. And also that in the min-max setting, you cannot avoid spurious non-equilibrium sets with positive probability. So, which means that you probably need to use some different approach, whether learning with mixed strategies, multiple time scales, adaptive methods, or what have you. And of course, some open questions. One question is whether this type of behavior arises in GANs. I don't have an answer to this. Whether some new structure, some hidden convex concavity structure, as in the paper by Flokas and co-author, can help in this regard, or if you need to go to second-order methods, or etc., etc. But I think there are already there's already a good number of questions, so I'll stop here, and yeah, be happy to take more questions.
Thank you, Panayotis.
Yeah.